Well, in the last video, we designed a simple low-pass filter, okay, with a RC circuit. So here we had the input, and from the capacitor side we took the output, okay, and that had some issues. Okay, let's take a look at the output figure. It kind of looks like this. Okay, you don't have to worry about the phase for now. So this was my output, and this was the input line, and this was my output. Okay, so this portion is called pass band. Lower to the cutoff frequency we call it pass band, that is we are allowing to pass, and the right side we have the stop band that we are not allowing to pass. Okay, so this was my cutoff frequency, and the range of frequency, that what we call the bandwidth. So it was starting from 0, so bandwidth is equals to fc for a low pass filter. Okay, now the slope that we have in this curve, that is the gradual cutoff, this slope is decreasing per decade is 20 decibel. Okay, so that is what we call and there is another name that we call 6 that is 6 decibel per octave. Okay, I will explain later what does actually mean. Now another thing is that you should know minus 3 decibel point, that is where we are actually saying that this is my cutoff frequency, not this 0 decibel point. No, after 70% decade, then we are getting the cutoff frequency. Okay, and we can actually calculate or fix the cutoff frequency by taking a particular value of resistor and capacitor. Okay, now let's go back to our discussion. So this was my first question, that how to build a filter, and we have done this. Now my second question that we actually now is that there are some issues with filter. That one is gradual cutoff, that is a problem. Okay, that was a problem. So if I have like 50 Hz signal and 500 Hz signal, they are very close. So if I have a gradual cutoff, then I will have some components from 500 Hz as well. This was my 500 Hz. If I have like gradual cutoff like this way, so I have this portion, that's something I don't want. Okay, I want like a cutoff of like this, I want a cutoff like this, so that this portion does not come. Okay, so I want a much more like a straight cutoff. Okay, and another thing is that the attenuation of the input signal. Okay, let's start by this one, gradual cutoff, how we can actually deal with this issue. Now here actually when we designed, we used one capacitor and one resistor. Okay, that means one network. In this network we have one resistor and one capacitor. Now we call this order of the filter. Okay, and there is another term that you need to know now, that is called order of filter. Okay, this is also very important, that is number of reactive component. Understand this very well, number of reactive component. Okay, so in this filter, the filter that we design, okay, I have one reactive component. Resistor is not a reactive component, capacitor or inductor. We are not dealing with inductor yet, I'll talk about that later. So I have one capacitor, so this one is a first order. Okay, this one is my first order, this one is my first order low pass filter. So we call it by represent it by n is equals to 1. Okay, now what if we are to add another branch, this branch, another simple branch, a resistor and capacitive branch? That means I had this circuit, so I add another resistor here and another capacitor like this way. Okay, parallel. Now I take the output from this portion, then I have two capacitor, so my order of the filter will increase to 2, right? My order of the filter would increase. So let's do that in our PSpice and see what do we get. I have this one, so I want to add another resistor, so capacitor, click R to rotate it simply, and I want one resistor. Okay, I just press another resistor. Okay, now connect these portions. Okay, so this is my new low pass filter. Let's take a look at the outputs. Now you can see this was my input, this red one, you can see this red one, and this is green one. So my red one is with n equals to 1, that is 1 capacitor. Okay, that means my first order low pass filter, I have this output, and with my second order filter I have much more like sharp. Okay, not still there is a curve but slope, but still it is actually better than this one. Okay, it is still better than this one. Now if we actually add another branch like this way, so let's see how do we have if we actually add another one. Okay, I place another resistor and another capacitor. Okay, now you can also copy, but if you copy, remember to change the name, otherwise it will show an error and you will just won't understand where is the error. Okay, 0.01 micro. So I have 3, so let's take another output from this passive voltage probe here and see the output now. Okay, so okay, now this is my output. So the higher the order and the higher the order, you see I am getting much more. Okay, like a straight line. Okay, it was much more slope, the slope was much okay. Now I am getting much more a straight line. So as you can see, but still as you increase the number of branches like capacitor, but it has actually from here to here there is much difference, but from there to there, second to third, there is a smaller difference. So at least for now we can actually say that if we increase the number of orders. Okay, if we increase the number of order of the circuit, that filter, and then that means we are increasing the number of reactive components, then we are getting, okay, rather than gradual cutoff the problem, we can actually get much more sharper cutoff. Okay, so that actually fixes my problem with that, right? Now you probably have noticed that as we increase my order of the filter, my cutoff frequency that was previously 1 divided by twice by RC, that was 1 divided by and twice by RC previously with n equals to 1, now has changed. Okay, because I have another resistor and another capacitor, it will change. So this will now become like this way. Okay, this will become twice by root over R1 R2, the two resistors that we used, and simply C1 C2. Okay, that will be my new cutoff frequency. Now there is another problem when you actually increase the order of the filter. Okay, there are some other problems that actually occurs. Okay, otherwise we could just keep increasing the order like n equals to 5, fifth order, then we'll have much more straight cutoff, but that is not something that we use. We normally use second order filter. Okay, this is the widely used normally, but we don't go for higher orders because it creates some another issue. The issue is this one, the attenuation of the input signal. And what is that actually? So let's move these portions out for now. Okay, now attenuation of the input signal. Previously I showed you that my output signals, that is my amplitude, right? Output signal is V input multiple divided by my reactance divided by my total impedance of the network. So you can actually automatically guess that the V output is always less than my V input. Okay, this portion will always be less than my V input, the input signal that we are feeding. Now that actually, this portion, this value actually decreases much higher. V output decreases and gradually, and as we increase the filter, okay, the V output decreases much more rapidly. Okay, V output decreases. That means, so say I have my you can imagine like this was my input voice signal, say mark it by 10. In the output side, when I am actually using a filter to truncate some portion, in the output I am not getting 10 anymore, I am getting 7. So my voice that was loud previously, now I am getting a much more quieter voice. If you actually increase the number of number of reactive components, that is increase the number of filter, it will only gradually decrease, and it will decrease, and that is something we don't want. Okay, we want actually cut off a portion, we want to truncate a portion, but without hampering my original signal. I don't want to decrease my original signals, voice signals amplitude. Okay, So that is something we have to deal with. That is my next problem, how to deal with this one. Okay, now so there is another thing that is like so here we can see, as we increase the order, okay, as we increase the order, and the amplitude, we call it gain actually. Okay, and the gain of my filter decreases. Okay, and it decreases at a rate of 1 divided by root 2 square root over 2 to the power n. Okay, so as you can guess, if we increase the n, it will decrease by this way. Okay, so for first order you will get 0.707, for n equals to 1, 0.707, n is equals to 1. So if we make it 2, it will become 0.05, 0.05 of v input. Okay, that will be my output. So it has actually decreased quite a bit. So it has already n equals to 2, it has already become half of my input signal. So we don't want to go any more further. Okay, now so another thing, so the question is how to do about it. That is what we are going to answer in the next video. But there is something I want to say again.